So we'll start part 2. We're still in this first part of the cell, talking about the plasma membrane and how things behave when they're crossing the plasma membrane. But what I want to get into now, there's a good reason for me to delay talking about osmosis until now. Until now, we've talked about diffusion of solutes, diffusion of stuff, like sodium or elephants, right? We just go from an area of high concentration to an area of low concentration, and that is always true for stuff. Unfortunately, water is going to do something a little bit different. Water is our universal solvent. Water is what stuff is suspended in. So water is going to have its own gradient. Water does go down its own gradient, but water's gradient is going to be opposite from the gradient of stuff. We're not going to consider water to be stuff. The way I'm using the word stuff, I'm using stuff on purpose. I'm not just being an idiot. There's a good reason to say stuff. So water is going to be the opposite of stuff. Water is going to go from an area where there's not a lot of stuff to an area where there is a lot of stuff. So the way I draw water's gradient, I've drawn this in blue. I'm kind of blurred. I'm not blurred out. I'm kind of translucent in my recording, so this might not be terribly clear. Yeah, you can see that all right. H2O is going to behave in an opposite fashion. Water wants to be where there is a lot of stuff. Water is going to go from an area of low concentration of solutes to an area of high concentration of solutes. So this is a pretty classic lab activity. What we have here is a selectively permeable membrane. We have some kind of solute that cannot pass through the selectively permeable membrane, but it does have enough gaps in it that water can go through this semi-permeable membrane. So water can move, the solute cannot. Now, if there were no selectively permeable membrane here, or this were a membrane that would allow glucose through, you know by the principles of diffusion that the glucose would move from this area of high concentration to this area of low concentration in the water, right? You already know that because you're already an expert in gradients. But because this is impermeable to glucose, while being permeable to water, the only thing that can move is the water. And the water is going to go to the area of higher concentration of glucose, because that's what water does. This behavior of water is called osmosis. Osmosis refers only to the behavior of water. And generally, again, we are talking about a semi-permeable membrane such as the plasma membrane. As I mentioned earlier, while water is polar, it is also very small. So over time, water will cross that plasma membrane. So this is the lab activity. You set up the water level the same on both sides of this U-shaped tube. You have a semi-permeable membrane. You add a lot of solute to one side, and you wait. You just set a timer and you wait. And over time, the water level is going to rise on the side of high concentration of solute, and the water level is going to lower on the side of low solute concentration. So that's a really classic experiment that demonstrates the simple concept that water goes to stuff. So the easiest way for me to conceptualize this is to tell you that water goes to stuff. Stuff goes from an area of high concentration to low concentration, but water goes from an area of low concentration of stuff, a low concentration of solute, to an area of high concentration of solute. What this achieves is equalizing the concentration. So before, this was very, very concentrated and this is very, very dilute. At the end, the concentration gradient is more equal across the water. Let's look at this a slightly different way. Yes, exactly. So this is a different variation of the same experiment. You put a lot of solute inside of this environment. You put a semi-permeable membrane on it, and over time the water is drawn into the area of high concentration, and the water level rises inside of this container and lowers inside of the rest of the container. That's the standard. Why is this important? Why do we care about osmosis? We care a lot about osmosis in healthcare fields in general, in nursing in particular. If you're the person hanging the IV bags ever, if you hang the wrong IV bag, you can kill somebody with osmosis. That's a big deal. So the way that you kill people with osmosis is messing with the tonicity of their blood and their cells. So what do I mean by tonicity? Once again, we're talking about stuff. There's a certain amount of stuff inside of the cell, and there's a certain amount of stuff outside of the cell. It's not perfect water out here in the human body. We have a lot of stuff. We have ions, we have proteins, we have all kinds of things going on outside of the cell, just like we have all kinds of things going on inside of the cell as humans. So in an isotonic solution, the concentration of stuff outside of the cell is the same as the concentration of the stuff inside of the cell. Yay! That means a certain amount of stuff will be drawn into the cell and a certain amount of stuff will be drawn out of the cell, and it's in equilibrium, so everything is healthy and normal, happy, we're all good. Isotonic is fine. If you have ever been around IV bags, if you're already in some form of healthcare right now, then you know the most common way to do volume replacement is isotonic saline. So it's saline that has the same tonicity as blood, as the interstitium, and as our cells. So we can't do any harm to our cells by hanging isotonic saline. No harm done. If we were to hang a bag of pure water, there's considerably less stuff in that water than there is inside of your cells. So you introduce water to the bloodstream, then you are introducing a hypotonic solution. So hypo means less than, lower than. So there's a lot of stuff inside of the cell. There's not very much stuff outside of the cell. Water goes to where the stuff is, which is inside. What's going to happen here is the cell is going to expand. The water is drawn into the cell, and it's going to blow up like a balloon until it bursts. So cells can burst in a hypotonic solution. So hanging that plain water IV bag killed a person by bursting all of their cells. Congratulations on killing a man. The other alternative is a hypertonic solution. So that means there is more stuff in the solution than there is inside of the cell. That means that more water will be drawn towards the stuff, which is outside of the cell. And this is going to dehydrate the cell and shrivel it. We still have a lot of organelles. There's a lot of physical stuff inside the cell. So it can't crumple away to nothing. It's going to crumple around the organelles. And that's why it looks spiky, because there's cytoskeleton, there's organelles, there's structural components of this cell. So a hypertonic solution can also destroy cells. They're not going to burst. They're going to become spiky and shriveled. But it's also very, very dangerous. Yep. That's, I think, the only thing that's appropriate to say for now. Isotonic, hypotonic, and hypertonic. There are cases where you would hang a hypotonic bag or a hypertonic bag, but that's nursing practice. That is well above my pay grade. That's just something to look forward to in the future.